postdoc at ID at HCD since January. First of all, thank you very much for having me, because it's a good opportunity for me to introduce myself. So in today's talk, I will discuss about designing human AI interactions using human-in-the-loop and explainable AI. So a few things about me. Basically, my background is in computer science and artificial intelligence, but my research experience and interests lie in the intersection of AI, machine learning, and human-computer interaction, focusing on aspects as user modeling and personalization in human-centered AI, with applications in healthcare and education. And here at HCD, I will also explore topics in future work practices. So this is the outline of the talk. I will begin with a short introduction about human-AI interactions and the current guidelines and frameworks. And then focusing on human AI and explainable AI. And then I will describe my work in some use cases for human-AI interaction, concluding with my ongoing and future work. So whenever you have any questions, please feel free to interrupt. So what is human-AI interaction? Human-AI interaction refers to when a user needs to complete a task with the help of AI support in a general way. In this paper, the authors have identified 3 types of human-AI interaction based on who initiates the interaction and how the user and the AI respond during the interaction. And based on this, we have intermittent, continuous, and proactive interactions. The authors in this paper highlight the need to focus on continuous and proactive interactions, since they seem to be the most complex ones. But we should have in mind that a mix of these interactions can take place during human AI. There are also other frameworks and guidelines that try to investigate different aspects of human AI interaction. In this one, the authors discuss about how we can design with machine learning, and they identified these 4 different value channels. And what this means is that they want to go from what ML is capable of doing to how these ML capabilities can actually be translated to human values. So, for example, AI can be used to get insights about our own self, or about the world, or how a system should be optimally performing, and so on. Now, in another framework, tries to categorize human-centered AI based on the different levels of computer automation and human control. And what they say is that the way that we can achieve reliable, safe, and trustworthy AI interactions is by achieving at the same time a high level of computer automation while maintaining also a high level of human control. Now, considering such frameworks and guidelines, there are also many more. There are also some toolkits that have been proposed to help designers design human AI experiences. This is from Microsoft, and they have also published a set of 18 guidelines for human AI interaction. And based on this, they developed this toolkit, which includes design patterns and examples that can be used to actually satisfy these guidelines. And I have highlighted here some guidelines that focus on explainable AI and human control. There are also more of them. From Google, we have the AI guidebook, which again it includes worksheets and tools that can help designers design AI systems. And they include, again, about explainability or how user can add feedback, can provide feedback to the system. And a similar one is again is the AI meets design toolkit, which follows a similar way to help designers. Doesn't seem very nice, but it can help designers plot the machine learning models that they want to use, and also address some of the most similar AI challenges. These are very useful toolkits, and they cover many different aspects of human AI interactions. But I would like to focus on these two methods for AI, because we want to focus on these two parts. First is how we can include human users to the decision-making and learning process of an AI system. And at the same time, we want AI systems to be able to,
Yeah, sorry. So it's very difficult to see the slides, but someone in the chat says that he has your slides from a previous time.
Oh, yeah, yeah.
Okay,
sure.
Shares the
slides? Yeah. So yeah, we will focus on human-in-the-loop and explainable AI, which describes how these two parts of the interaction can communicate with each other and exchange information. So from the one hand, we have human-in-the-loop AI or interactive machine learning. There are many different, different terms for the same thing. Essentially, what interactive machine learning does is to include the end user to the learning process. And this can be done to help users get a better insight of how a machine learning system works and how it makes predictions. And they can guide this underlying machine learning process to either improve the model or satisfy their own needs. And it has been used, for example, for personalization or to increase motivation of users during the interaction, as well as to enhance trust. And it's interesting because this term has been around for a few years. As we can see, this was one of the first times that it was kind of coined as a term. And in this thesis, it is also mentioned as socially guided machine learning, because this author argues that in order to be able to teach a machine, you have to establish kind of a social interaction with the machine. And here we can see also that we have the transparency aspect of machine learning. And this can happen during different stages of the machine learning. We can have users, for example, to be involved in the data processing, if the data processing part of the pipeline, as well as during the model design, training, and evaluation. But also, interactive machine learning can be used during the interaction. So we will have an AI system that acts autonomously. A user may be able to supervise and monitor the system and intervene with feedback when needed, for example, to ensure safety. So here are some examples of interactive machine learning for different purposes. We have this one from 2003, and back then the authors proposed interactive machine learning in order to facilitate the image segmentation problem, which back then was a complex problem for computer vision. So they showed by having a user in the process, it could facilitate the learning and actually to generate accurate classifiers for segmentation. And here we have a robot learner and a human teacher. And the teacher provides feedback and guidance to the robot to learn how to build objects through basic shapes. So the user here explicitly tells the robot what to do. In the case that we have here, which is a social robot for language learning, the student provides feedback to the robot implicitly. So the robot learns how to personalize its affective behavior based on how the user, if the user is engaged or not. So here we can see that we have different types of feedback that the user can provide to the system. And in a more recent case and more complex case about autonomous driving, in this paper they investigate different aspects when a human user is involved in the learning process. For example, they investigate if the system should start with a pre-trained model or start from scratch, or how users can actually be used to facilitate this cold start problem, as well as how user is supposed to give feedback. Is it going to be continuous or intermittent, or there are many different ways? And this is, of course, this depends on the expertise and the intentions of the user. So we need to take lots of things into consideration before putting a human in the loop. So these are some points about interactive machine learning. So we need to investigate at the same time. Yeah.
Can I ask a question, if I don't interrupt the flow of your story too much, about the previous paper?
Yeah.
I haven't read it, but I'm just curious in terms of the human control over this. Can you say a bit more about what is being learned by interactive reinforcement learning? So
Yeah.
you know, is the goal to then take the hands off the steering wheel after a while, because it has learned many more situations to be coped with, because the human trains the algorithms rather than the algorithms need to be trained by the environment? Or anyway,
Yeah.
Could you say something more?
Yeah. Through a simulation. So they try to investigate how the user can provide feedback during the interaction to improve the model. Because if the model is how it's autonomous driving. So here is how the car will avoid other cars in a simulation. And the user, what does is to be there in the interaction, and when needed, to tell them the reinforcement learning agent what to do. If they have to, the actual actions during so the system is autonomous and the user is there and trains the system when needed.
Yes, I think I get it. Okay, thanks. I'll read the paper and please continue.
Yeah, so these are some points that we need to consider for human in the loop. Is how machines actually can learn from human input, and how humans can provide good feedback to the system. And we have different types of feedback, such as evaluative feedback, or labels, or to give the system the examples and demonstrations of what the system has to do. And we also talked about implicit, explicit feedback. It can also be mixed. And one basic consideration is how to minimize users' workload, because user can be always there and tell the machine what to do, but that could result to extremely high workload. So on the other hand, we have Explainable AI, which has become extremely famous this last years. And in general, the goal of Explainable AI is to enable AI systems to self-explain their internal models, decisions, and predictions, and to do that in a human, understandable way. Also, for Explainable AI, a very important thing is who is the target user of Explainable AI. And as we can see, for example, in this graph, if you are a data expert, you may have different purposes of using Explainable AI. And there are different design goals as well as different evaluation measures. For example, a user that doesn't know what AI can do, Explainable AI may be used, for example, to enhance user trust. But for AI experts, it can be used for model debugging. So we have also different evaluation measures. This work also tries to identify who needs Explainable AI and why. And here we can see examples, for example, that users that are affected by model decisions need to understand their situation and verify their decisions. While regulatory agencies may need to certify the compliance of a model.
Oh, sorry.
Yes, no, it's safe.
Please go
It's okay,
ahead.
it's okay. No, it's fine.
Yeah.
So in this slide, we see three different terms, which are interaction concept, explanatory goal, and interaction goal. And in this paper, the authors tried to match the interaction concept with the interaction goal and the explainable AI goal. For example, if the interaction concept is to transmit information between the AI and the user, then this is the interaction goal, that users need to see accurate explanations, and the goal of the explanation is to achieve transparency. So based on this, I would like to highlight these two parts, that we have explainable AI, that it can be used for trust, for debugging, for different ways, but also explainable AI can enhance users' perception and understanding for their own behavior. Because AI can learn many things about us while we interact. So by presenting these user models to us, it can help us enhance our own self-perception. But also it can enhance users' perception about the system capabilities. So based on this, I would like to briefly present three projects, three use cases that use AI in a different way in terms of how users interact with AI. Here we have the cognitive assessment system, where the user, the child, passively interacts with AI. That means that they don't have any control over the AI decisions. In the next case, we have a social assistive robot that learns to adapt to the user based on users' feedback. So user participates in the personalization process. And at the third case, we have explainable AI that is used to enhance users' cognition. So let's see how this happened. So this was a multidisciplinary project to design a cognitive assessment tool for children. More specifically, it was for embodied cognition, and that was how to measure cognitive assessment through exercises, through physical exercises that also have cognitive demands. So the idea was that the child performs a set of predefined exercises, and computer vision and machine learning is used to analyze this motion and assign a score to the child. And this is how the framework of the system was, actually how the process of training the AI model was. First, we had to collect data from many children, then extract the videos and features, and then we had the very tedious and really consuming process of annotation. So what we need to do there was to see the videos, score the children based on the cognitive assessment tool, and then feed this to the learning algorithm. That seemed much easier before we started doing that. But manually annotating was very, very hard, and it was most of the times not in accordance with what the machine learning system would do. So briefly, what I did here was to implement a graphical user interface that visualizes the data that the system gets, so it could help non-technical users to score the child, to score the participants as the machine learning would do. So that was in order to get reliable annotations from non-technical experts. And this interface could be also used for active learning, for example. So if the system didn't know how to do a prediction, it would ask for the label from the user. Now, on the second use case, where user has a little bit more involvement in the learning process, that was actually a cognitive training task using a social robot. The robot would announce a sequence of letters, and the user had to remember this sequence and use the buttons to repeat these letters. And the robot would adjust the difficulty of the next task, so the length of the string of letters, and also the verbal feedback to the user. And interactive reinforcement learning was used to make this personalization using both the performance of the user as well as engagement as it was measured by a Nietzsche headset. And the problem was how to combine these different types of feedback in order to achieve personalization. And so in order to achieve also safety, we also did a user study for secondary users. So we assume that there's a supervisor, maybe a teacher, who supervises this interaction with the robot and a child. So we built this interface that visualizes both the user model of the user and also what the reinforcement learning decides for the next round. So the supervisor user could agree or disagree with reinforcement learning, and this could be used again as training feedback for the system. Now, for this, we did a comparison study with a personalized robot and a not personalized robot. Results were very nice for me because a personalized robot was perceived as a more intelligent trainer, and also users performed better with a personalized robot. But what was really interesting was during the interviews with the players, they highlighted some aspects for explainability and autonomy. There were, for example, players that asked me, okay, but how does it work? And why the system gave me a harder exercise? So it could be, maybe it would be nice to explain, to give this explanation to the user. And also in terms of autonomy, Some users told me that it would be nice if I could select my own level once in a while. So that has to do with human autonomy. And also for the interface, for the supervisor, a proper visualization of systems perception and decisions can surely enhance human decision making. So these were the messages from the takeaway messages from the study.
Can I ask you a question? You said performed better compared to what? What did you compare in this study?
It was a comparison study, so half of the users used the personalized robot that learned how to personalize the difficulty, and the other one was giving random difficulty levels. So the users that followed the personalized training session performed better in terms of the score.
You didn't compare to expert trainer who adjusts the level?
No, it was just the score from this game. Each player had to play 10 rounds, and at the end of the 10 rounds, we So for the third use case, the goal was to build an explainable AI system to support self-regulated learning. Self-regulated learning is how to enable students to self-control their learning process, self-assess their skills, and become more independent learners. And this was the framework that all the information that can be used through machine learning and AI, for example, student modeling and user profiling, could be explainable and used in order to support specific self-regulated learning skills. So for an example for this framework, I developed a prototype game for cognitive training. So here the user could select their own task to play for the next round, and it could be a combination of different cognitive exercises. So the more complex the combination is, the more harder the task is. And what we want to investigate is how to use explainable AI as open learner models and explainable recommendations to help the child choose appropriate levels. So what we would do is that here we have actually the open learner model of the child. So it's what the machine learning part learns. And based on this, it can give the child a recommendation for the next task. So the goal of explainability at this point is persuasion. So we need to persuade the child why this next task is appropriate for you and what the outcome of this would be. And because we're talking about the children, we needed to find an appropriate way to deliver these explanations and these recommendations. And we followed some persuasive strategies. So how to deliver this message. Here we have an example of authority. For example, that your teacher says that you could do that, compared to an example of social proof that your friends prefer this task. But the idea is to use the recommendation system output and formulate this persuasive recommendation. And this, it was actually with master's students during a project, again in the same idea about self-regulated learning. And this included the design of an educational avatar that is used to depict the future self of the child in a week. So the idea is that the student does the planning on their own, their weekly planning, and then they kind of discuss it or negotiate this plan with their future self avatar. And this is the architecture. So the student can set daily goals. The underlying machine learning makes the predictions and makes the predictions for this model. And the idea here was how we can visualize these outcomes through the design of the avatar. So for example, if the user would set an optimistic goal or something that the avatar, the machine learning could detect that this is not feasible, it would show an avatar that is kind of confused. So based on the model's confidence or model's uncertainty, this can be used as a design feature for the avatar. And here are some other examples from master course. It was a course for design, industrial design, and the idea is how to design explainable AI for education. And here, if you can see, it's for online lectures, so that the teacher could get an estimation of how engaged the students are, and showing something like a blob on their screen. The other one is a prototype for a robot that could simulate how the student feels. So the student could check the robot to kind of self-reflect. Also for brainstorm, so this device would go to the people that need to speak more, for example, during a brainstorming session, or to the more dominant ones to understand that, okay, maybe I have to speak a little less. And also other nice applications, for example, about sign language learning. And here we see that we have a robot that is the instructor. And if you can see here, there is a bar that shows actually the uncertainty of the machine learning model to give feedback to the user, immediate feedback about how they can correct or improve their sign. So we discussed about explainable AI and interactive machine learning, and my goal is to see how this can be combined and kind of unified to design interactions. Because I see that explainable AI can be used to provide information from AI to the user, while interactive ML or human-in-the-loop AI can be used to provide information from the user to the AI. And this combination can lead to, that's my argument, to better human-AI interactions. And we have different challenges that we need to face. For example, how we can design transparency or explainability, or how we can design interfaces that can be used from humans to provide feedback. And this combination of explainable AI and human-in-the-loop can also lead to what they call hybrid intelligence. So here we have explainable cognitive intelligence that comes from human, and explainable AI that comes from the AI. Here we have other examples of how hybrid intelligence can be defined, and we have different goals of hybrid intelligence. For example, here we can see that in order to integrate knowledge from both sides, it's different when we have decision support. So there are different actions that take place. But it's again the loop of explainability and interactivity.
Sorry.
Yeah.
Could you please turn off the lights?
Yeah. How?
Yeah. Well, there is nothing more. Yes. To draw.
Good.
Yes.
So yeah, currently our work is to kind of realize these possible interactions in the context of future work practices. So to see how different types of users in the workplace can interact with AI and what could be the possible reasons for this. For example, in a team of employers, explainable AI could be used to provide a shared understanding of how the team works on a specific task. Or, for example, the team can provide feedback to the AI that can be transferred to the supervisor. So, for example, if there is lots of negative feedback within a team, this uh, should be visible to the supervisor. So, and that's the last part. This is what we aim to do now, is to actually make a study, a design workshop to define some low-level actions that users and AI can do during the interaction. For example, by providing either correct labels or by providing numbers, that is an evaluative feedback, or demonstrations for the model. And from the other side, we have AI interactions, which is how to provide the model output, which is the prediction, or to provide different explanations. And the idea is that it's not very visible. The idea is that by having such primitive actions, to design interactions for a given purpose. I can give you some explanations here. Here we have a user that is a job applicant, and this is a case for a CV assessment. So the machine learning is used to say if this applicant will be accepted or not. And here, a user scenario is that we have a user that is rejected. So we see how the user can ask for explanations from the system and how the system can provide explanations back to the user. And for example, this design pattern here could be the concept of contesting an AI model. So what we want to achieve through this workshop is to see if designers can use such interaction cards to start from primitive actions to go to high-level intentions. And that's the last slide. So the goal here is both in terms of design. So if we can identify such design patterns between explainable and interactive human-AI interactions, or to see if there are new types of interactions, but also to get insights about what are the computational challenges when we want to implement such a collaborative interaction. For example, if we have feedback from different users, how can we weight this feedback for shared autonomy and so on? So by considering also concepts of co-performance, because we have both parts participating actively in the interaction, and co-adaptation. And I think that would be all, and thank you very much.
I have a question. Well, apart from, sorry, the mess and the speaking, you know, the project where you were assessing, well, the study where you were assessing the cognitive learning of children, I guess, for with body, yes. In the later slide, you say that then you were, next one, here, providing the assessors for the manual labeling. with how the model would interpret that, or so like a sort of support to code as the model would do, right? This is what you said.
Yeah, yeah.
And then, but when the model didn't know how to label, you would ask people. So
Yeah, that's for a future. That was just for annotation,
okay.
but it could be used.
Okay. Because I was curious if you can explain more. Why do you need the manual annotation?
Yeah.
If you can explain that better, and
Okay, so for example, this task was during this task we observed the position of the legs.
Yeah.
So the child, for a given task, they had to go either left or right based on what they see in the screen.
Okay.
So as humans, we knew that, for example, this one is a correct step.
Yeah.
So we would label it as a right one, or so on.
Yeah.
But sometimes, and due to children's motions, it wasn't very easy to either manually give the labels if it was a correct movement or not. So by also visualizing the data.
So you mean that the model could understand better if the
movement
was correct or not?
Here we didn't have a model.
Yeah.
It was just the annotation phase. So we would just watch the child and kind of annotating each single movement. Still, that was really difficult with just a human person. By visualizing the data, it made it more difficult for the human annotators to annotate the data. And as a later step, after we had a model, the model could automatically detect this, but if there was an issue with the data, it could ask, okay, can you give me the label for this one? Because I'm not certain. Or
thanks for the presentation. Good to meet you like this with content straight away. One of the questions that was going around in my head is, how do you, in your studies, assess the behavior of the people that you're interacting with? So sometimes you give anecdotal evidence of how people change their behavior or not. And one of the things I find fascinating is behavioral adaptation to systems. And so how does it affect the way you then interact or learn or disengage or engage or get confused or etc. etc. And so my question is, how do you do that? So how do you test for the behavior? Could you comment on that?
Yeah. For example, for this case, which was the most complete because I also did the final user study, and I just focused on how they perform, if they were engaged during the interaction.
The self-report?
It was both from this headset, easy headset, but also self-reports. So I tried to collect both self-reports and objective data, and to kind of make a story out of them. It wasn't just a single measure, because and that's the interesting part. If we could be able to find behavior indicators, it would be interesting to see also how explanations, for example, affect users. Or
So we should have a chat anyways, but one of the things that's in the back of my mind is the work of Emma van Zoelen. She's supervised by Mark Neerings. So this idea that you also touched upon in the end, emergence and co-adaptation of maybe co-learning, is something that she investigates. So kind of how do you assess the patterns that bubble up in terms of doing something, not doing something, checking, do and wait, people getting frustrated, or all these kind of observations of what actually happens with a, in this case, it's an agent, it's not a physical system, but an agent that's learning. Anyways, I was just struck by
no, that's
the way that she assesses that.
This is the
evident.
this is work.
Even I think
This is work.
co-learning or.
Yeah, no.
But yeah, that's very interesting.
Also, I have to excuse myself. I have a master graduation, so I need to be in time.
Thank you.
Thanks.
Meanwhile, we have a question from Radi, who is joining us virtually. Do you mind unmuting the speaker there so Radi can ask his question?
What's the mark?
It's on mute.
Maybe the voice.
Yes. Please go ahead. Ask your question.
I don't think he can hear me from here. Can you?
You're muted.
Ask his question. Because he's muted now.
Radi? Yes. Would you like to ask the question yourself?
You ask the question.
Oh, yes. Okay, I can just read. Where is the show conversation? No.
He didn't post the question, he raised his hand.
Yeah. Thank you for the presentation, Kostas. So, somewhere in your presentation, you spoke about uncertainty, and that got me thinking about how humans in general make their decisions or provide their inputs in an ambiguous fashion. So, for example, in the scoring of a child project that you had, you said that annotation was a little bit of an issue, and it's quite likely that there was some ambiguity, both inter-annotator as well as possibly intra-annotator disagreement. So my assumption would be that Bayesian methodologies are one way to handle this kind of ambiguity by modeling the distributions. But of course, the downside is, again, a point that you mentioned, that the computational challenges around them might be so high that you can't really do human-computer interaction in that. So in our work, we're trying to, for example, do interactive segmentation on CT images of the head and neck area. And usually over there, the contrast is so poor that a lot of times your AI models fail because they can't see the contrast between one tissue and another. But then we're trying to extract uncertainty, which is very time consuming, and we also want them to do interaction. But then we can't really expect our clinician to like hit a button and like wait for like probably 10 seconds and for the input to come in. So is there any hallmark work within literature that has, even at a smaller scale, used Bayesian uncertainty and interaction together?
I don't have something in my mind right now, but specifically about Bayesian ways.
Okay.
Because I think it's maybe it's really related to the use case and what the purpose of the human is. Because, for example, here just a simple measure of uncertainty, which is a parameter of the machine learning model, could be useful for the human annotator. But in other examples, maybe we need more complex ways. I'm not sure how to.
All right.
Respond, but
okay, thank you.
Thanks.
I have a relatively technical question. So it's about the FutureMe project. Could you go to that slide, and I'll also share it. This one. So could you talk a little bit more about the model? So I think that the model is actually depicted on the right.
Yeah.
So this is the model that predicts the requirements of the user, but then how complex is the data that feeds in the model, and what exactly does the model do? So I suppose it's a neural network, right?
Yeah.
Yeah. So can you explain a little bit more?
Sure. Yeah. We haven't implemented that, but from the literature we found a similar model. It's a recurrent neural network, and the input for each node, it's the time spent for each one of the 4 subjects. For example, we have English, Dutch, geography, and so here it would be the input from the student, so how many minutes they want to study for each task, and the output would be a number to say the number of completed exercises.
Right.
So, and we have it as a recurrent neural network, so kind of its node, its level, it's 1 day of the week.
Okay.
So we would like to see for the weekly plan, what would be the weekly progress.
Okay.
And the data is kind of simple, so it's not a very complex task. So yeah, that's why we proposed this one. And recurrent neural networks have been used for student modeling and with such data.
Okay. I was just wondering, would you see any kind of value into going into a more of explicit models of how students engage with the tasks? So try to see if you can, I don't know, it's almost a swear word these days, but how about rule-based models, which could just, describe what exactly the students do, how they turn the training time into the result. So my question, I guess, is, do you really need a neural network here, or?
Yeah, I agree with
this
you.
one? Yeah.
I mean, if the else rules work, it's totally fine. Again, the explainability would be the same, more or less. But yeah, still machine learning can capture events that you cannot like code with even else. Even if you follow a model for engagement, or there may be students that are not described by certain models.
Right.
So that we propose the machine learning model, which is data driven. So,
and you mentioned you did not implement it.
Yeah, that was more as a design project.
Okay, got it.
So we focus on.
I'm also wondering how you get the data from this.
Yeah, that would be through a user interface. So, for example, we would give students to like forms to write down their intended plan and what they actually did, and use this data for the model. So initially without the avatar and the whole system.
Okay, but then, of course, when you collect this data without the whole system, then this data only is valid while you are not using the system. And when you use this data for as an input to the system, then the whole learning process changes. So it might be that the data that you use.
Yeah, it depends on because for this model, it could just say if I kind of follow my own schedule.
Mm-hmm.
So it's not, because the interaction with the avatar is only during planning. It's not while doing the exercises or.
Okay, thanks, nice.
No, I think we are finished also. Good.
Let's see.
Thank you very much. Yeah. No?
Okay.
Okay, thank you again.
Thank you very much.
I'm so sorry, I messed up with the camera.
It helped me stick there.
Yeah, you couldn't move too much. Okay.